This conference will now be recorded.
At this juncture, I take immense pleasure in inviting our resource person, Mr. Prasanna Ramamurthy. So, in spite of his busy schedule, he accepted our invitation in presenting his knowledge on his aerospace communication towards the students in this webinar. So, I welcome all the participants to share his knowledge to the maximum extent. Okay, so let me have a brief introduction about our resource person. Mr. Prasanna Ramamurthy received the BE degree in Electronics and Communication Engineering from the University of Madras, Chennai, and ME degree in Avionics from Madras Institute of Technology, Chennai. He started his career as a system engineer in Park Controls and Communication in 2003. Thereafter, he worked in Avia Systems and Airbus Defence and Space as a system engineer for aircraft missile management system and surveillance radar systems. He worked for Defence Research and Development Organization India from Avia as an avionics system engineer and contributed in avionics upgrade programs for MiG-27 and Su-30 MKI aircrafts and the development of AEW and C systems. He joins the Collins Aerospace Bengaluru in 2016 and has been a specialist avionics system engineering. His areas of research includes future air navigation and air traffic management, wireless sensor network for aircraft application, integrated vehicle health monitoring system, and aircraft data analytics. Prasanna received Performance Excellence Award from DRDO for his contribution towards MiG-27 avionics upgrade program. He has 6 US patents and 3 international publications to his credits. Prasanna is an in-course certified system engineering professional. He is an executive member of in-course India chapter, working on creating awareness in the industry and academia about the system engineering and promoting the practice of system engineering as a discipline in the engineering and technology organizations in India. He is a member of SAE Health Monitoring Committee and is currently working on the development of ARP, Aerospace Recommended Practice Guidelines for verification and validation of integrated vehicle health monitoring system. I welcome Prasanna Ramamurthy for this webinar on aerospace communication system. I welcome you, Prasanna. Now the session is yours. Over to you, Prasanna.
Thank you, Dr. Raja. So that was a great introduction. So good afternoon, everyone. So thanks all of you for joining this session. First of all, I would like to extend my thanks to the Department of Eshwar College of Engineering for giving this opportunity. And so my special thanks to my college friend, Dr. Raja, who has reached out to me in this regard. And so this is something that we have been discussing for quite some time. And so finally, the time has come for you. So the topic we originally planned was on aerospace communication system. I have made a small modification to that. I have made the topic as aviation communication systems. The reason being, the content that I'm going to present today and share with you all is going to be specific to aviation. So when you say aerospace, it consists of the aviation as well as the space components. And it will be difficult to cover both the topics in a shorter session like this. So that's the reason I thought of covering the aviation communication system specifically during this session. Maybe if we get another opportunity, we can plan for another session on space communication exclusively. So this topic, I feel it is more relevant in the current situation that we are all going through. And so we have all been experiencing the need of communication in the recent times. So even this webinar itself is enabled by the advancements that we have achieved in the communication technologies in the recent times, right? And so the communication as a subject as a concept has been an integral part of the human life right from the beginning of the human race. So though there are many changes and evolution in the ways and means of communication that have happened over a period, and in recent times there are a lot of technological and innovations that have happened in the communication domain specifically. Right. So irrespective of that, the communication as a concept and technology still plays a major role in our life, and we are finding new way of communicating and new ways of using that communication for purposes, which we call communication. So in this regard, aviation also is not an exception, definitely. The communication plays a major role in the overall aviation sector, starting from the aircraft operation. Starting from the aircraft's operation, including its flight, including its ground operation, and the airport operations. In the entire aviation ecosystem, the communication technology plays a major role. So that is what is going to be the focus of this presentation. So now let's get started with this. So before getting into the specifics of the aviation communication system, I thought of giving just a brief overview on the aircraft systems overall, because many of you may not be having the background on the aircraft technology and aviation specifically. And so you have been specialized in electronics and communication. But again, out of your own interest and enthusiasm, you guys may be following the advancements and developments in aviation. But considering the benefit of the overall participants, so I thought of spending few minutes on giving an overview on the aircraft and the systems that are present on aircraft and the role played by different systems. And after which we can get into the specifics of the communication system in particular. So you can see the aircraft over here. And so when you see an aircraft from outside, okay, so we are aware of the purpose of different parts or the components which are visible outside. Okay, so people who have traveled in an aircraft, so you might have observed the engines which are mounted on the wings, and you might have peeped into the cockpit of the pilot, so from where he is controlling the overall aircraft. Okay, and after you get inside the passenger's cabin, you may be seeing different systems, including the lighting systems, the communication systems, and so the passenger addressing system and seats. Okay, so there are different components that are present on an aircraft from nose to tail. Okay, so some of them have been marked over here, but these are just the indications or the highlights of the major systems that are present on an aircraft. You can see here in the front, we have the complete cockpit system, which consists of various displays and controls that are used by the pilot to control the overall. And so we also have the communication, navigation, and surveillance systems, okay, so which are primarily working on the RF and microwave technology. And again, inside the cabin, you have various cabin systems, including the lighting system, air conditioning system, seating system, and so on. And again, so you can see that there are a lot of electronic systems and electromechanical systems that are present on aircraft. So in order to operate all these systems, you have a fundamental requirements. You need to have the electrical power. Okay, so that electrical power generation is a major component on an aircraft. Okay, so generally this electrical power generation is coupled with the engine itself. So there is a generator coupled with the engine, so which generates the power and which is distributed to all the electronics and electromechanical system all over the aircraft. Okay, in addition to that, you can see there are cargo systems basically to handle the passenger cargo, and so there is an in-flight entertainment system, so for the entertainment of passengers who are traveling in an aircraft, and lavatory, okay, so the restrooms and toilets. So though they are very trivial and So we don't pay much attention to those but on the aircraft, so this is also a very important system which consists of many um, involved technologies. Okay, we are not going to discuss about the details of all those things, but this is just to give an overview of what all things that an aircraft consists of. Okay, so of course the engine is going to be a very key system which is going to give the propulsion to the overall aircraft and which ensures um, the movement of the aircraft from its source to destination in a smooth manner. So what are the enabling technologies of the overall aircraft operation? So we discuss what are the systems that are present over there, okay? And so we can categorize the overall the aircraft systems and technologies into these major categories. Okay, so the first and foremost is the structures and aerodynamics. So the body of the aircraft needs to be designed in such a way that yes, it can fly smoothly in the atmosphere or the air medium. Okay, so to design this, the structure of the aircraft, so there is a separate subject called aerodynamics, so which studies the movement of aircraft in the air, and it also deals about the effect of various aerodynamics forces on the aircraft, and so how to design an aircraft's structure or body to handle those aerodynamics forces in order to ensure a smoother flight. So that is what this is dealing about. Okay, and again, to ensure the aircraft's flight and its control, so there are a lot of control surfaces on board. So I might have seen that so when after the aircraft taxis on the runway and before takeoff, there are many control surfaces on the wing, so which are either extended or retracted. And similarly, during the landing also they are being operated. And again, during the flight, so whenever the aircraft has to take a turn or whenever the aircraft has to climb, there are some control surfaces on the wing and also the tail of the aircraft which are being operated. So these are very critical for the aircraft's the overall movement and its altitude and attitude changes. So the structures and aerodynamics basically deals with this domain. And next comes the propulsion. So we already discussed that the engine plays a major role in providing the required thrust to the aircraft to achieve the required motion, whether the forward motion or the vertical motion. Okay, and the thrust generated by the engine combined with the aerodynamics forces provides the required lift to the aircraft in order to raise in the air, to go up and down, and also to make the different maneuvers, either taking a turn or pitching up or pitching down or banking. So all these things are controlled by these two technologies. And next comes the electric power. Okay, so as we discussed that we need the power to operate all this electrical and electronics and electromechanical system, and the generator system which is combined with the engine generates the required AC power, and again it is integrated with a sophisticated power conversion and distribution system, because there are different types of electronics and electrical system operating on board, which requires different types of power and with different ratings. So some require AC power, some require DC power, some operates at 115 volts, some of them operate at 5 volts. So there are different power requirements from different aircraft systems, so which is being met by this electrical power generation and distribution system. And next comes the landing gear. So this is a very, very crucial system because this ensures the safe landing of the aircraft on the runway, and also it plays a major role during the takeoff and taxi. The environment control system. So once you go up in the sky, so as you go, means as the altitude increases, we all know that the temperature changes, the pressure changes, and the human body is not designed to survive in those climatic conditions. So as we cross different layers of atmosphere from troposphere to stratosphere, so the pressure, density, and the temperature of the air mass changes around us. So there is a need for maintaining a constant temperature and pressure within the aircraft. Okay, so for the benefit of the passengers or the human beings who are traveling on the aircraft, and also for safeguarding the various electronics and electrical systems on board, because they are all designed to survive or operate in a specific range of temperature and pressure. Okay, so that is the role played by the environment control. So you can compare this to the normal air conditioning system that we use in our homes and offices or colleges. Okay, but again, this is much more complex and sophisticated, considering its purpose and so the wide variety of needs it serves. And the last comes the avionics. Okay, so this is where the communication system that we are going to discuss today comes into picture. Okay, so the communication systems are just part of avionics. It's not the full avionics. So we will talk more about what is in avionics. So avionics basically covers all the electronics and electromechanical systems that are available on board an aircraft. Okay, so there are various sensors and control systems and displays, communication systems that are required for the overall operation of an aircraft. Okay, so you can see here some of them are listed over here. Okay, so first and foremost is the aircraft state sensors. Okay, so basically the pilot has to be aware of what is the current state of the aircraft. So if you take the example of driving a car, the driver needs to know what is the speed or some basic parameters about the vehicle's movement, right? So primarily we look for the speed of the vehicle, and so we look for the mileage and the fuel efficiency, and we look for the engine RPM. So whatever is critical for driving a car is provided in the driver's dashboard inside the car. Similarly, even for the aircraft, there are different critical parameters that needs to be made available to the pilot for him to effectively control the aircraft. For example, since the aircraft is going to have a third dimension, which is the vertical dimension. So in addition to the speed and the orientation, the pilot also needs to know the altitude of the aircraft. So basically the altitude, speed, and also the orientation of the aircraft, whether it is climbing up or climbing down, whether it is pointing up or down, or whether it is banking on the left or banking on the right, or whether it is taking a right turn or a left turn. So all these things need to be known to the pilot for him to effectively control the aircraft. So that is what we mean by aircraft state sensors. So in addition to that, the navigation is another important system. So when we are on the ground, nowadays we have started using Google Map in order to navigate through the unknown territories in the urban areas as well as in remote areas. But so before the Google Maps, we all used to do the visual navigation, right? So we used to look for the landmarks, and that's how we navigate and find the new places and travel. But when it comes to the aircraft, so there are no landmarks available when you fly in the sky. Okay, so in all 360 directions, you see only the blue sky and the white clouds. So there are no visual. So the visual navigation becomes impossible. So when you are flying an aircraft, so that's where the role of the navigation systems comes into picture. So here again, we use different kinds of navigation, including GPS. So GPS we use even for the ground applications. So even on our Google Maps, GPS is the underlying technology. So similarly, even on aircraft, GPS is one of the primary navigation system. But in addition to that, there are other navigation systems based on the radio technology and also the electromechanical technology. So we have the inertial navigation system, which is primarily based on optical and electromechanical technology. And so the radio navigation systems were the legacy ones. So these have been in use right from the advent of the aircraft in 1903. But so in spite of the arrival of GPS and other modern navigation systems, the radio navigation system still play a major role due to their reliability and well-established infrastructure available for that. So in addition to this, the pilot should also now know about his external environment. So we spoke about the aircraft's the movement and the aircraft state and the navigation. So when we talk about external environment, so when the pilot is flying in the sky, so he needs to know what are the other aircraft which are flying in his vicinity. So in order to be aware of the traffic around him so that he can effectively avoid the traffic and also avoid the collision and accidents. Okay, so there are different types of sensors used for that, which we call as surveillance systems. And so irrespective of availability of all these things, unless so we get the data from this and make them available to the pilot visually, so the pilot won't be able to use them. So that's where the role of displays come into picture. So if you see in the modern aircraft cockpit, so you can see here there are n number of displays, LCD or LED displays present in the cockpit, providing different information to the pilot. Okay, and you can imagine the amount of the effort the pilot has to put in order to read each of these displays and understand and interpret so what is being provided on those displays, and based on which he has to take a decision for ensuring a safer flight. So that way you can say that the pilot has a tremendous workload when he is present in the cockpit, because especially in a passenger aircraft, he is responsible for the life of hundreds of people on board. So he has to ensure a very safe flight. So that way the stress levels and the amount of workload on pilot are enormous on a passenger aircraft. Okay, and you can see that so what you are seeing here is just a small portion of the cockpit. So apart from this, there are thousands of controls all around him. So both in the front, on the left side, right side, above his head, below his head. So he has to control all these things. So in order to make sure that the flight is safer from source to destination. So this is where the role of avionics comes into picture. Okay, so in the olden days when the technology had not developed much, so you can imagine that he definitely wouldn't have had all these high-fi sophisticated digital displays. Okay, so he was provided only with the electromechanical dials. So all the parameters were indicated through the dials, like how you see in the car. You can see in the cars, we just have very limited information. Maybe we see just 2 or 3 dials. But in order to present the data, whatever you are seeing here on this glass displays, on an electromechanical display, you can imagine how many such dials we need to provide on the cockpit. And you can also imagine the amount of effort the pilot has to put, so in order to understand and interpret those things and fly. Okay, so this is what has been made easier by the advancements in avionics technology. Okay, so we can say that the pilot's workload reduction is one of the achievement of the avionics technology. And in addition, it also plays a major role in improving the aircraft's performance and control. Okay, so in earlier days, the aircraft was flown purely with the mechanical control system. And you guys who are following the automobile technology, especially the operation of cars closely, so you might have come across how the cars were controlled in the earlier days and how they are controlled right now. So if you take the earlier Maruti 800 car, that was purely based on the mechanical control system. Okay, so from the steering to the gears to the wheel, everything was linked through the mechanical links. There was absolutely no electronics or electrical controls available over there. But whereas if you see in modern cars, so the control is very smooth and handy, and it is made very easy for the driver to drive a car. Okay, so nowadays we are talking about even the auto drive cars. So what made this possible is basically the introduction of the electronics into the controlling of vehicles. The same thing has happened even in the case of aircraft, and the fly-by-wire technology was introduced in the mid of 1980s, so which had revolutionized the air traffic control and which has made it much easier compared to the earlier control systems. So the other thing is the reduction in fuel consumption. Okay, so when you fly at different altitude, the fuel consumptions vary due to the variation in the pressure, density, and temperature of the atmosphere, and the fuel burning characteristics vary from altitude to altitude. So there are intelligent systems present on the aircraft, so which takes into account all these parameters, and it calculates and provides the right trajectory to be followed by the aircraft in order to optimize or improve the fuel consumption. Okay, so in addition to that, as we discussed, the avionics provides increased safety. So when you have a better control over your aircraft, definitely it automatically improves the safety of the aircraft as well. And again, the air traffic controls. Okay, so the air traffic in the national airspace is controlled by the air traffic control towers which are present on the ground. So in every airport, you guys would have seen the air traffic control which provides the clearance for the takeoff and landing of the aircraft. They not only control the takeoff and landing, they also control the traffic after the aircraft takes off and reaches the cruise altitude. So the communication with enter the airport and exit the destination airport that happens. So all these things are basically enabled by the connectivity between various entities that we spoke about. Okay, so we are going to discuss primarily about that connectivity part. Okay, now before entering to the core, the communication, the aviation communication part, so let's discuss some maybe the basic or philosophical questions. Okay, what is connectivity and what is connectedness? Okay, so let me just put in simple terms. I don't want to complicate these things because this calls for a lot of involved discussions, so for which we don't have time. So by the word connectivity basically means the infrastructure that is available to enable the exchange of data between the multiple entities or at least two entities. So that is what we call by connectivity. For example, if you are having the internet connectivity at your home, so basically what it means is, so you have taken the connection from one of the service providers. So he has routed the cable to your house and he has installed the Wi-Fi router in your house and it is ready for your use. So that is what we call as connectivity. Basically the infrastructure is ready. But unless we use that infrastructure for a purpose, that connectivity is not going to be meaningful. So let's say that you have taken the connection for your home and you have locked the home and you have traveled somewhere else. So that means basically that connectivity is not being used. So the connectedness comes into picture when basically we use the infrastructure for certain purpose, right? So at home we use the connectivity for various purposes. Now means it has become almost impossible for us to live without the connectivity. Means we can live even without food nowadays, but not without connectivity. So the usage of that connectivity for certain purpose. Okay, we watch the web series on the TV and using the connectivity, and on the phone we use the connectivity, and for our online classes and for our work we use. So there are different applications of this. Okay, so when you use the connectivity to share and get connected to the different people or different systems, that's where the connectedness comes into picture. Basically, the connectivity is being used for certain purposes. That's what we call as connected applications. So the connectivity basically enables the information sharing, and it also shares the awareness. So it gives an awareness about our surroundings. Okay, so either within the house or outside the house or across the world. So there are different levels of the situational awareness that we get through the connectivity. And again, also for performing any activities, the command and control is very important. So once you get some information, so how do you use that information and how do you convert that into an action? So what is the purpose of having the connectivity in office? So for example, now we are having this webinar. So there is a purpose. So this technical talk is the application that we are talking about, right? And the connectivity provides the increased speed of command. So the speed of command in the sense in how fast, how quickly we are able to perform the action that we want to, that we intend to do. Okay, now let's come to the aviation world, the aviation communication systems world. Okay, we spoke about various systems on board the aircraft, and we also spoke about different activities that are happening on the ground. And again, in order to perform these ground activities, again, there are multiple systems involved, right? For each of the functions, and there are multiple vehicles and multiple decision-making systems, multiple or a variety of communication infrastructure starting from cellular or Wi-Fi, which are being used. So there are multiple technological elements involved in providing the infrastructure for performing these activities. And again, all that infrastructure are connected through some means so that so they coordinate with each other very well and perform the action smoothly. For example, as soon as the aircraft lands and reaches the gate, there is a sequence of operation that has been already defined. Okay, so the first set of activities performed by a team, and for example, the aero bridge is connected to the aircraft's door, and the passengers come out. And after that, the cleaning happens. Then the maintenance activity happens in parallel, and the cargo, the baggages are unloaded in parallel. And again, so once the passenger goes inside the airport, so if it is international travel, then there is a different queue available for immigration check and all that. So all these things are already streamlined. But in order to coordinate this, in what sequence it has to happen, so every entity in this should be aware of the status of the other one, whether the previous step has been completed so that the next one can start, or the passengers can go through the next step. So the connectivity plays a major role on the ground system. On the aircraft, as we discussed, there are multiple sensors and multiple controls. So unless there is an interaction between the sensors and controls, the flight operation is going to be impossible. So even though the pilot is in the loop, there are many things which are done automatically by the machines, basically the digital computers on board. So they collect the information from the sensor and they process it, and they provide the information to the pilot or through the display, and based on which the pilot decide what action needs to be taken, whether to increase the speed or decrease the speed, or go up or go down, or take turn to take the direction, or change the direction. So all these decisions are taken by the control, and it's again executed through the controls. So when he operates the control, for example, the joystick or the throttle, so the command has to go to the respective executors. Basically, it has to go to the engine to increase the speed or decrease, and the command to change the direction has to go to different control surfaces which are on the wing and tail that we discussed earlier. Okay, so all these operations, both on board and off board on the ground, everything is enabled through the connectivity. And again, so there is also a need for the communication between the aircraft and the ground, even when the aircraft is in the flight. So there are a lot of things which are getting exchanged between aircraft and ground. For example, the air traffic control, which is present in the airport. So they provide the direction to the pilot to avoid the traffic and follow the predefined flight plan or flight path. So there needs to be a continuous communication between the ATC and the pilot, which is enabled by the air-to-ground connectivity networks. Okay, so this is an overview of what are the different communication components that are involved in the aviation ecosystem. So now we'll get into a little more details of this. Okay, so we will start with intra-aircraft communication. Basically, what are the communication means or the communication technologies which are used for the communication within the aircraft. Okay, so most of the sensors and controls that we spoke about earlier, they're all primarily connected through the wired interfaces at this point of time. Okay, there are different types of wired interfaces which we'll discuss now. most of those wired interfaces are already standardized. So for each of those interfaces, the standards exist. So basically the industry standards define the last 3 layers of the OSI model 7 layers for the computer networking. I think those who are into networking, I think definitely the computer science students would have studied about the computer networks in one of your subjects, and I'm sure even for EC this will be one of the subjects. If you are in initial years, first year or second year, you may be studying in future. Okay, so basically the OSI model is something like the Bible for the computer networking. Okay, so it defines different layers of operation for the network and what are the different elements that needs to be present when you establish a computer network. And so in the case of avionics, and most of the functions are controlled through the computers. So even the aircraft has utilized the advancements in the digital technology, and it is completely computerized, and they're all embedded control systems which are operating and functioning on the aircraft. So you can consider avionics as a digital avionics consisting of hundreds of computers which are connected to each other. So basically the avionics network is a computer network. So you can take it that way. So in that sense, so the standards of the wired interfaces, which we generally call as data buses, so they define the last 3 layers of this OSI model, whereas the rest of the things are left to the individual application. So we spoke about flight controls, we spoke about flight management. They're all different applications. Okay, so and each of them have different requirements for these upper layers, starting from transport application. So those things have been left to those specific applications, whereas the last 3 are almost standardized for a given aircraft: network, data link, and physical layers. And so in order to define or design avionics data bus, so these are certain communication design parameters which are taken into account. Okay, so you have to choose bus control methodology. Okay, so there are different methodologies available, and in avionics specifically we use these 2 things. The bus system is either a command response, a master-slave concept, or it is a token passing, which is basically a decentralized control method, whereas the first one is the centralized one. And in terms of topology, so we have over different types of topology like linear network, ring network, switch network. So these things you guys would have studied in your computer networks subject. And again, media access protocols. Okay, so we spoke about the definition of data link layer, right? So the data link layer again is divided into 2 sub-layers. One is the link layer and the MAC layer, media access control layer. So the media access control layer, the MAC layer, defines this multiple access protocol. Basically, this controls the ways in which the physical communication medium is being used by multiple computers. So when multiple computers try to use the same medium for communication, so when they try to use simultaneously, there are chances of the collision of packets and loss of packets and all that stuff. In order to streamline the sharing of the communication media by different computer resources, so these multiple access methodologies or protocols have been defined. So the popular ones are the time division multiple access, frequency division multiple access, carrier sense multiple access, and so code division multiple access. So the last one is something that which is generally used in wireless, but not for wired interfaces. So I don't want to get into the details of these things because the purpose of this session is not to get into the fundamentals. Okay, so basically just to give an idea. So when you read these concepts as part of your subjects, then you should be able to relate to what we are discussing here. And again, addressing concept. So when multiple systems are sharing the information, so there should be a source and destination, and we need to have a mechanism to identify the source and destination. So that's what is handled by this addressing concept. So we have a physical addressing concept and a logical addressing concept. So in physical addressing concept, each node or the computer is assigned a specific address. So whereas in logical addressing, so the computers are not really assigned, means mostly this communication happens in a broadcast or multicast mode. And based on the type of information that is present, the computers pick up the information that is relevant to themselves. For example, if I'm sharing information about the navigation and weather and the flight control on the same bus, so some system may be interested in only in the navigation data, so it will pick up only that data. So basically, the logical addressing identifies the type of data that is being transmitted. So just by looking at the type of data, the respective systems pick up what they are interested in. So that is what we call as logical addressing. Then, of course, we need to have error detection and correction mechanism. So in order to ensure the communication reliability. So generally, most of the avionics data buses use the parity mechanism, either as a single or double parity. Both odd and even parity concepts are being used here. And in some few odd limited systems, or even the FEC is being used, forward error correction. And signaling type, so they follow either the voltage signaling or the current signaling, and some of them use the optical, wherever they use optical fiber as a medium, so the optical signaling is used. Physical medium, so copper and optical fiber are predominantly used. Line coding, so this is basically how do you represent the individual digital bits in terms of signals. When you transmit the signals, the bits in the electrical signal form, how do you represent that? So that is what is being defined. There are different methods here also, return to zero, non-return to zero, biphase coding. Okay, so all these things are chosen based on the nature of the physical medium that you choose. So normally the copper twisted pair medium that you choose is considered as a band pass channel, right? So basically it will not be able to handle the DC components. So in those cases, normally the biphase coding or the non-return to zero methods are used. And again, when you want to attach or connect a new system to the common network, there are different coupling mechanisms available. You must be studying a subject on transmission lines and control. So where you'll be studying about the stub matching, right? So whenever you want to connect one of the load or a node to that general transmission line, you have to match your impedance with the characteristics impedance of the transmission line. Okay, so that is the concept that is being used over here. Okay, so that's about means the different the aspects that are being considered when you define a wired data interface for an avionics application. Okay, so apart from that, there are different design drivers which are also being considered. So the first and foremost is the communication reliability. So the avionics system that we discussed, they are all safety critical system, because any failure in those systems can lead to catastrophic accidents, the serious damages to the aircraft as well as the human life. So those things make the avionics system highly safety critical system, and they need to be designed with a high level of reliability and design assurance. So the communication reliability is a major factor in the design of communication system for avionics. And throughput, so definitely it has to manage the amount of the data traffic that is expected for a given network. And weight of the communication system is the primary concern on aircraft, because as you see here in the highlighted text, so every pound or every kilogram of weight that you add to the aircraft, that automatically leads to the fuel inefficiency. So the fuel consumption automatically increases in proportion to the weight. So for every 1% reduction in weight, basically we can achieve 0.75% of the fuel consumption. We can save 0.75% of fuel. So that is a thumb rule. So the weight is definitely a major factor. And so the communication network or the protocol that we define should ensure that there are a minimum number of components and minimum wiring so that the overall the weight of the communication system remains lesser. And apart from that, the system and component reliability, as we discussed, so the communication components, the transmitter, receiver, and the physical cable that is being used, and the couplers, and all these things should be of very high reliability and very high quality, so that so they meet the objective of the aviation security and safety. And so this is just a summary of different wired interfaces, the data bus standards that are being used on aircraft. Okay, so the MIL standard 1553, this is very popular in the military aircraft and it is very highly reliable. So we'll be discussing about some of this one a little bit in detail, not in more details. Okay, so ARINC 429, this is primarily used in commercial aircraft, and ARINC 629, ARDX. So all these data buses are primarily used for commercial aircraft. Okay, so let's start with ARINC 429. So if you look at this, this is defined as a point-to-point the communication network. Okay, so you have a transmitter and there is a communication line emerging out of a transmitter to which we can connect up to 20 receivers. So each transmitter can handle 20 receivers, and again for transmitter to receiver it is a point-to-point link. Okay, and again here we use a logical addressing. As I said that so the receivers or transmitters are not assigned a physical address. So depending on the type of data that is being transmitted, so the individual receivers pick up what they really want. And if you look at the data rate that is achieved by this, it is means there are two different data rates, 12 to 14 kbps and 100 kbps. So if you compare this with the speed that we are talking for the Wi-Fi and our broadband connection, it is much lesser. But so you have to consider the fact that it is a point-to-point network. So you can have hundreds such transmitters and receivers on the aircraft, and so you can have different subnetworks handling different group of systems. So that way means the data rate provided by this system is more than sufficient to handle the traffic that is intended for those smaller subgroup or subnetwork of computers. ARINC 629. So again, this is not a point-to-point. This is a kind of linear bus concept. So wherein you have different terminals connected onto a linear bus network through the current coupling mechanism, and so the multiple access protocol being used here is a combination of the TDMA and CSMA, the time division multiple access and carrier sense multiple access. So the carrier sense multiple access is something which is similar to what you have in Ethernet. So basically what it does is whenever a given computer transmits the data, and even if the other computer also transmits the data at the same time, the collision happens. This collision is detected by the individual computers, and so they try to retransmit the data maybe after a certain period of time, which is influenced by an algorithm. In a similar way, even in ARINC 629, so we have 3 different timers defined as part of the protocol, which is available in each of these terminals. And so those, with the help of those timers, the system ensures that there is no collision, even though the individual terminals are allowed to transmit and receive in both the directions. Based on the time division multiple access concept, with the help of those timers, the collision between the data is avoided. And here you can see that you can achieve a data rate of up to 2 megabits per second. So this is a MIL standard 1553B, which is used in the military aircraft. Here, if you say, it is based on the master-slave concept. It's a centralized control. You can see here that there is a centralized bus controller which controls the operation of the entire network. So there are remote terminals which you can call as end systems or end devices. Okay, and the data exchange between any of these remote terminals is completely controlled by bus controller. The bus controller dictates or commands, so who has to transmit and who has to receive at what period of time. So that way, actually, it follows the time division multiple access uh, protocol for the channel access, and it has a data rate of 1 megabits per second, and it is half duplex. That means that at any given point of time, only one-way traffic is allowed. Means simultaneously, the systems can't communicate in both the direction, both in transmit and receive direction. And it deploys a Manchester biphase coding and voltage mode coupling. And so the major drawback of this system is a single point failure. Means, as I mentioned, the complete communication is controlled by a single bus controller. So if this bus controller fails, then the complete communication system fails. So which is not really acceptable. So in order to overcome that drawback, basically what they go for redundant bus controllers. Means instead of having a single bus controller, so they go for either dual redundant or quadruple redundant bus controllers, so which takes care of the failure, single point failure aspect. Whereas in the previous thing, if you see in the Ring 429, so there is no problem of that single point failure. Means since it is going to have multiple subnetworks, so even if one transmitter fails, only that small subnetwork is going to get affected. It is that failure is not going to propagate to other subnetworks. Whereas in this case, it is a different case. Means there is no subnetwork concept here. It's a single network which is controlled by a centralized bus control. And so the modern database that is being used in some of the aircrafts like Boeing 787 and A380 is the avionics full duplex switched Ethernet. So this has been derived from the industrial Ethernet protocol that we normally use for our LAN and internet connections. Okay, but the problem with the commercial Ethernet is that its reliability. As we discussed, it is based on the collision detection and avoidance protocol, CSMA, carrier sense multiple access. So which doesn't ensure the reliability of the transmission. Means you can't ensure the on-time delivery of the data packets to the destination. Okay, so this non-determinism makes the Ethernet unsuitable for avionics application, which are highly time sensitive. So if the data has to reach at a given point of time, it has to reach at that instance. Otherwise, it can lead to different chain reactions. It could lead to multiple failures as well. So considering that, so they customized and adopted the Ethernet to make it suitable for the avionics application, and by introducing the concept of avionics full duplex switched Ethernet. So in this case, actually, so they have something called the AFDX switch, which is equivalent to our Ethernet switch, what we use in our LAN, and we have the end systems, which are basically the computers with the respective the AFDX transceivers. And if you see the data rate, it supports up to 100 megabits per second. So that makes it more suitable for all the advanced avionics applications. So that's why it is being used in the latest aircrafts like A380 and Boeing 787. And so another advantage is it also reduces the number of wires that is being used, because now the communication is kind of distributed as well as centralized. So you can see there are multiple hubs which forms like a sub network. So that way means you need just very short cables between the end systems to the switch. So that makes that considerably reduces the length of the wires as well as the weight of the wire that is required for the overall network compared to a Ring 429 protocol. So another popular one is a CAN bus. Okay, so this is very popular in the automotive than aerospace, and this is again based on the broadcast type communication. So you have the different CAN nodes which are connected to a common bus, and every node transmits data to, means it is broadcasted to everything. Means there is no addressing concept here, and this also follows the principle of logical addressing. So every node picks up whatever data it is interested in based on the transmission from others. And again, so whenever there is a conflict between two systems, when they try to transmit the data simultaneously, so they use something called arbitration based on message priority protocol. So every message is assigned with a priority. Okay, so the high priority messages are given importance, and automatically the node which with the lowest priority message waits for the completion of the transmission of the highest priority message. So that's how the handshaking between different nodes happen on this canvas. So again, here you can see the data rates vary from 125 kilobits per second to 1 megabits per second. And again, it is limited by the cable length. So as the cable length increases, your data rate automatically falls. Okay, so far we discussed about the wired communication, and in addition to that, we also use the wireless networks. But again, the primary difference is the wireless networks are only used for non-critical systems and application. So we discussed about avionics, and we also discussed about the cabin systems, right? So the avionics fall under the category of the high critical system, because their operation is very crucial for the safety of flight. Whereas the cabin systems are non-critical systems. Means even if your the in-flight entertainment display fails, it's not going to affect the safety. Means it might cause some inconvenience to the passenger at the most. Okay, but it is not going to pose any threat to the safety of the aircraft or the passengers. So that way, the wireless networks are currently being used only for this non-critical application, because there are a lot of challenges which needs to be handled and overcome before this wireless technology matures for using it in avionics communication. So currently the first step has been taken by using it only for the cabin systems. So you can see here the Wi-Fi that we use normally at our home, the same technology is used for the cabin network, through which the passengers can access the internet. And it is also being used for the in-flight entertainment. So whatever programs that are displayed on the terminals, so they are also migrated to the Wi-Fi technology. So we have both 2.4 gigahertz and 5 gigahertz technology that are being widely used. Though the 2.4 gigahertz is a dominant one, so 5 gigahertz has just made an entry, and so definitely we can expect growth in the coming days. So all the remaining specifications are same as the standard Wi-Fi specification that we have. The data rate it supports is 122 to 720 megabits per second. Again, the 720 is for the 5 gigahertz mode of operation. 2.4 gigahertz supports 120 to maybe up to 240 megabits per second. And it has a complete support for the internet protocol based routing and also the dynamic host control protocol support. So the another protocol that is being widely used is IEEE 802.15.4, and so which is primarily used for the low power sensor networks. Okay, so this is not as fast as Wi-Fi network, and so wherever the sensors which are operated based on battery and which can't afford to consume very high power, the battery operated sensors are definitely sensitive to the battery life, so they have to consume minimum power. So for such applications, so this protocol is being used. We can see here it is basically used for low power, low data rate networks. And so naturally the data rate supported by this network also is much lower. So the maximum data rate that you can achieve is the 256 kilobits per second. And Bluetooth, anyhow, all of you must be familiar with this. So there is no difference between the Bluetooth that we use in our mobiles and what is being used on aircraft. And again, the purpose also is going to be the same here. So this is used for the short range communication, for accessing the data from the cockpits, either the cockpit system or the cabin system, to our individual electronic gadgets, either an iPad or a phone or a tablet, whatever it is. Okay, so now we've finished about the communication that happens inside the aircraft. So let's talk a little bit about, let me do a quick time check. So can we take another 10 minutes?
Yes, you can take.
Okay. So we spoke about the air to ground communication link, right? So we need to exchange the data from the systems that are on board aircraft to the systems that are on the ground. For example, the airlines control and the airport operation and also the air traffic control. So these are the primary stakeholders. So who receive the data from the onboard systems of the aircraft. So this is facilitated by different communication data links, or basically they are communication transmitters and receivers which are present on board aircraft. And again, they have a corresponding transceivers infrastructure established on the ground as well. So as you see here, there are three primary communication equipment or the communication system that are used for this purpose. One is based on the VHF, the very high frequency data link. The other one is the high frequency data link. And the third one is the satellite communication. So the communication that happens through the satellite. So these three are the primary means that are currently being used. So coming to the other side, so you see the central equipment, which is called the Communication Management Unit, CMU, so which controls the exchange of data between these onboard systems and the ground system. So this means you can consider this as a onboard aircraft router. Okay, so which basically receives the data packets from various systems and routes those data packets to the ground through the communication media that we discussed, either VHF or HF or SATCOM. So you can see here, so the CMU is connected to the VHF data radio, okay, so which basically transmits to the VHF data link, and you have the HF data link, and also you have the SATCOM transceivers, transmitters and receivers. And you also have a control unit through which the pilot will be able to select the data that he wants to send through this communication means. Okay, so basically it can be used for the texting, messaging. So when you say texting, messaging, not like our WhatsApp chat. So this is related to the operation of the aircraft and also for the communication with the air traffic control. So these are very highly critical messages, so which need to be exchanged between the pilot and various stakeholders. Okay, so just an overview about the VHF data link. So as the name indicates, it operates in the very high frequency range. So normally we classify the 30 megahertz to 300 megahertz as the VHF range. And whereas this system specifically operates in the range of 117 to 137 megahertz range. And again, this has a definition of those three layers what we discussed: the network, link, data link, and physical layer as per the OSI model. So this is primarily used for exchanging the data between the pilot and the air traffic controller through another protocol called ACARS, which we'll be discussing in the subsequent slide. Okay, and it is also used for sharing the data and information with the airline control. So the airlines who are operating the aircraft, so they always need to be in touch with the pilot most of the time. So this VDL or the VHF data link is being used as one of the media for that. But again, the limitation of VHF data link is that it is a line of sight propagation, as you guys know. So due to which the range of this communication is very limited. So unless you have the ground transceivers which are distributed at regular intervals, so the continuity of this data link cannot be maintained. Basically, the communication with the airlines through this data link cannot be maintained, especially when the aircraft is flying over the ocean, oceanic routes. So you can't expect to have the ground transceivers installed over the ocean, right? So that makes the challenge makes it challenging for communication over the VHF data. And so coming to the multiple access, this also uses a CSMA, carrier sense multiple access, because multiple aircrafts are going to use the same channel. okay, for the communication. So again, here also you need to ensure that the sharing happens in a smoother way. So the CSMA is being used. Okay, and you can see in the physical layer, so it uses the 25 kilohertz band for the communication. The channel bandwidth is 25 kilohertz. And so you can achieve a data rate of around 31 kilobits per second. So you may be wondering why the data rate is so low. Okay, so there is a thumb rule in wireless communication, right? So you have two critical parameters. One is the range, the other one is the data rate or the throughput. So if you have to increase the range, so you have to reduce the throughput. And it is not possible to increase both at the same time. So though means there are different methods which helps in achieving different ratios between these two parameters. But so general thumb rule is that if you want to have a longer range, then your throughput automatically reduces. And again, if you want a higher throughput or the data rate, then you can do it only at the shorter ranges. Even if you look at our home Wi-Fi, the 5 gigahertz mode offers a very high speed, right? So you can achieve up to 400 or 500 megabits per second with 5 gigahertz, but it doesn't provide the range. So if you move from one room to another room, so you lose the connectivity and automatically it slows down. Okay, so basically what it implies is that you can't achieve longer range when you want a higher data rate. So the same thing applies here. You can imagine the range to be covered, okay, by this communication links from the aircraft to the ground. It is really long. So the data rates are limited by this basic principle of communication. Okay, so this drawback of VHF, means which is limited by range, is to some extent overcome by the high frequency data link. Okay, so the high frequency generally falls in 3 megahertz to 30 megahertz. Again, here also, if you see the bandwidth is very limited, 3 kilohertz to 48 kilohertz is the typical bandwidth that you get for these transmissions. So automatically the data rate also is highly restricted, even in this case. So with the next generation high frequency data link, the maximum data rate that we can achieve is 240 kilobits per second. But the major advantage of HF data link is it is not relying on the line of sight communication. It uses the ionosphere for achieving the longer range communication. So I think this concept also you guys would have studied when in the radio wave propagation, right? So the ionosphere basically consists of the ionized atoms which has the free electrons. It's highly ionized. So which makes the ionosphere layer as a reflective medium. Basically, the ionized layer that reflects the electromagnetic energy. But again, it doesn't reflect all electromagnetic energy. Okay, this is also frequency sensitive. Okay, certain frequencies are getting reflected totally, and when you cross certain limits of frequency, very high frequency, then it doesn't reflect them. So it just allows those frequencies to pass through. Okay, so some of them just gets absorbed. Okay, so the behavior of ionosphere depends on the level of ionization that happens. So the level of ionization again varies between day and night. Okay, so during the daytime, there's a high level of ionization, and you can see that there are 4 different layers to which it is splitted into during the daytime. And the topmost layer, the F2 layer, is a highly ionized one. So whereas the lower layers are so gradually less ionized. So during the night time, you can see that the F1 and F2 collapse to a single layer called F, and so the D layer completely disappears and the E layer is present. So basically, essentially, the F1 E layer are primarily used for this HF communication, and mostly it is the F layer which is very useful for this HF communication. So you can see here, you have to tune your frequency to achieve a given range. So based on these variations, unless you have the knowledge of these variations, it is difficult to achieve that. So in the olden days, what happened was, they didn't have the means or the technology to have this knowledge. Though the theoretical studies through the long-term observation, all those things have given some model, but it is difficult to understand this one. So what they used to do is they used to do the manual tuning. So manually they used to try different frequencies. In whichever frequency they get the signal or they're able to establish the link, so they get tuned to that. But again, as the aircraft's location changes, so even this behavior changes. So it was the HF communication, though it was advantageous in providing the long-range communication. So the managing, the tuning, and also the quality of communication remained a challenge. But with the latest technology, so they are able to have the robust models of the ionosphere. So the software will be able to predict the variation of the ionosphere variation in different parts of the world at different points of time, day and night. So based on which it automatically tunes the frequency, the optimal frequency to achieve a given range. So that makes it more robust, and it also makes the modern HF system much reliable compared to the earlier ones. So the next one is the SATCOM. Okay, so SATCOM also is another means of achieving the long-range communication like HF. So irrespective of all these advancements, so the HF is still facing the problem of the reliability and also the quality of communication. Okay, so which is again overcome by the satellite communication. So here, so there are three elements. Okay, so we have a constellation of communication satellites revolving around the Earth, providing the full coverage of Earth from any point of from anywhere on the Earth. You will be able to access a few of those satellites, and that's how the satellite system is designed. And so you have the communication equipment, the transceiver on the aircraft as well as on the ground. So from the aircraft, the data packets are transferred to the satellite, and then again from satellite to the ground. So this ensures highly reliable communication, and also the low level of latency, and the quality is much better compared to HF. But the primary drawback of this is it is very expensive, because the satellite constellations are maintained by a private company or a service provider. Okay, so who charges for every packet that you transfer through these satellites. Okay, so that makes it expensive. So the airlines generally have to make a trade-off between HF and SATCOM, which one they want to use for what purpose. Okay, so basically the non-critical data, they use HF. Okay, so where they are not really worried about the latency and the reliability part, so they use the HF, whereas SATCOM is used for very sensitive and critical data exchange. So just to give an example, so there are different satellite systems that are being maintained by different companies. The popular ones are Inmarsat and Iridium. Okay, so again, the satellite constellations are also of two different types. So one is based on the geostationary orbit, and the other one is based on the low Earth orbit. So the geostationary orbit, basically the satellites are placed at a fixed position above a given geographical location on Earth. Suppose if we launch a geostationary satellite for covering the Indian subcontinent region, so it remains more or less in a same geographical location with respect to Earth, so it doesn't move. Whereas the satellites that are placed in the low Earth orbit, so they keep their relative position keeps changing. So if you observe one satellite at this moment of time, maybe after 1 hour, if you see, it may not be visible because it might have moved to a different place when it is placed in lower Earth orbit. Whereas in geostationary satellites, so they are remaining at the same position. You will be able to see them at any point of time from a given geographical location. So the Iridium satellite constellation, so there are 66 satellites in 6 different orbital planes around, revolving around the Earth. Originally, it was designed with 77 satellites. So that's a reason for it to have the name Iridium, because Iridium is an element which has an atomic number of 77. Since this also had a 77 satellites originally, so this was named after the atomic element, so the element Iridium. So this operates in the Ka band, okay, for inter-satellite communication, and it uses the L band for ground. L band is basically 1 to 2 gigahertz, whereas the Ka band is, I think it is 18 gigahertz to 27 gigahertz. That's the range. And so this has slightly having a higher bandwidth. And if you look at the data rate, again, the data rate is more or less same as what we had in HF communication. In fact, it is little lesser, but with some advanced modulation techniques, we have the scope of improving this data rate. And the multiple access, we have the TDMA and FDMA, which are extensively used. And they also use the QPSK and BPSK modulation for the waveform generation. Okay, so I don't want to discuss too much on this. Basically, we discussed about the types of data that is exchanged between the pilot and the controller. Basically, the air traffic controller provides a clearance for an aircraft to take off and land in the airport, and also they provide the guidance to the aircraft during the flight. So which direction they have to take, which speed they have to fly, and which altitude they have to fly at. So all these instructions are exchanged between the ATC and the pilot. So we have a dedicated unit called controller pilot data link communication. Okay, so this is a display terminal which is used by the pilot to send and receive the data from and to the air traffic controller. And this again operates through the data links that we discussed, primarily the VHF data link. And another equipment or the protocol that we have is the ACAS, okay, so Aircraft Communication Addressing and Reporting System. Normally, the salary or the payment to the crew, both the pilot and the cabin crew on the aircraft, is decided by the number of hours they spend in the air. And so after the aircraft takes off, how many hours they fly in the air. So that defines the crucial payment component of the pilots and cabin crew. So the airlines are very conscious, and they want to accurately measure this time so that they can optimize their expenditure towards the salaries. Okay, so this system, ACAS system, was primarily defined for that. So earlier, what they used to do was they used to manually report their time of means once the aircraft takes up. So immediately they call the airlines and manually say that yes, we have taken off. But the problem with this is that it is prone to the human error. Okay, so you may not be accurately able to measure. So sometimes they may be communicating after 1 or 2 minutes after the aircraft takeoff, or maybe much earlier. Sometimes there may be malpractices. Okay, even before the takeoff, they can call up and say that yes, they have taken off. So all these inaccuracies were possible. So in order to avoid that, they wanted to automate this reporting. So that's how they introduced this ACAS. And again, this ACAS connects to VDL, HTL, or SATCOM, any of these data links. And though ACAS was primarily used for this timing measurement and reporting purpose initially, later on it was also extended for sharing the message between multiple stakeholders like ATC, AOC, and airline administrative control. Whereas the CPDLC is specifically meant for pilot to ATC alone, not with anybody else. You can't use this for communicating with anybody else. Whereas ACAS can be used for using with others also. But again, this equipment belongs to the airlines, whereas the CPDLC is dedicated to the air traffic control. So that's the primary difference between these two. Okay, and so this is the last part. So now whatever the data links we discussed, whatever applications that we discussed related to the air-to-ground communication, they all follow different protocols in the legacy system. So each of them had different definitions of their physical layer, MAC layer, network layer, and so there was no standardization among them. And when you come to the ground network, so on the ground, the airlines control with ATC, and airlines communicate with other stakeholders like catering and ground handling crew and all those people, right? So they needed to have the ground communication network in order to exchange the data among all these stakeholders. So all these systems were having multiple types of communication interfaces and protocol definition and all that. So basically, it led to the higher cost of developing such systems. Okay, so the airline community decided to standardize all these things so that there can be a standardized end-to-end connectivity among both air segment as well as the ground segment. So that gave rise to this aeronautical telecommunication network. So in this case, if you see, primarily the three lower layers, what we discussed, the network, data link, and the physical layer. So they're basically the network and data link. So the physical layer still remains different because still this network is going to use the VDL HF SATCOM, because that is what is forming the physical layer for air-to-ground communication. That's going to remain the same. But at the network and the data link layer level, so there is a standardization, high level of standardization. So nowadays the TCP and IP are the very popular protocol when it comes to the local area networks and the internet communication. So they took the advantage of that, and they have defined similar protocols even for the airborne segment. So that way, at the transport, network, and the data link level, so you have a completely standardized way of exchanging data, both on the aircraft component and also in the ground network component. So this has made the maintenance of the network easier, and addition of new applications or new systems easier. And this also made the supply chain very effective, because means people, once they have the standard definition of things, so they can develop the system as per that, and the integration becomes much easier with the standardization. So that is the advantage provided by this aeronautical telecommunication network. Okay, so this is again another representation. Okay, so how the standardization has been done. You can see here the TP4. TP4 is equivalent to the TCP/IP, what we use in our LAN, and again the CL&P is equivalent to the IP layer, what we have. Okay, so that's about this, and so I'll take another 5 minutes just to talk about what we do in Collins Aerospace. Okay, what we are and what is our role in developing the communication systems that we discussed. So Collins Aerospace as a group, if you see, we develop the systems, all the aircraft system from nose to tail. Whatever you see here on this picture, all these systems are in our product portfolio. We provide the end-to-end solution for our airline customers. So we develop avionics, we develop the engines, we develop the engine controls, we develop the seats, we develop the cabin connectivity solutions, and we develop the landing gear, we develop the power generation and distribution system, and we develop flight control, you name it. So we have all those products, and we also develop the displays and controls for the cockpit. Okay, so one short video on what we do in communication. Okay, so we are
Hello, and welcome to the postgraduate program offered by the Mekong School of Business.
I run a program here called Global Connect. We provide a platform that can allow aircraft to connect to the ground, and then allow that ground platform to connect back to
the screen is not visible.
And we're there to help them move lots of data.
The screen is not visible.
Oh, screen is not visible? Okay, just a minute. How about now?
Okay, fine.
It's fine?
Yes, fine.
Here called Global Connect. We provide a platform that can allow aircraft to connect to the ground, and then allow that ground platform to connect back to an airline's back office. And we're there to help them move lots of data. In a lot of ways, what's happened on the ground and other technologies. I mean, at your home, think about your Nest thermostat or your connected door lock now at this point. It's putting sensors and technology and all kinds of things that weren't connected, and then connecting them together, and then doing really cool stuff with all the information that you can gather, like remotely turn on and off your AC. The same thing is coming into aviation now. We really are the only ones who can provide the range of hardware, products, aircraft parts, electronics, avionics, electromechanical structures, as well as services from the sensor generating the data on the aircraft, both about how it's performing, and then connecting passengers so they've got better in-flight entertainment experience, connecting pilots so they've got more real-time data. They can connect back to systems on the ground that can help them fly the aircraft smarter. It's about connecting various systems on the aircraft so you can monitor the health or the performance of the aircraft in real time. So Collins is uniquely positioned to take advantage of the connected aviation ecosystem. I love working on new stuff. Absolutely, it's very challenging. It can be very messy. You can have some false starts, but our job is to go out and do it credibly, learn something new, and then bring it back and turn it into excellence in delivery and excellence in product development. And excellence that shows with our customers, so that we can really carve out that leadership position in what is a new space. I would say it's stimulating, exciting, challenging, all at the same time.
All right, so that's about what we are doing. You could have seen that. So we provide the end-to-end solution when it comes to the communication and connectivity, both for the airborne and ground segment. Okay, so this is just a brief profile of the company. So we have around 70,000 employees all around the globe, and out of which 16,000 are engineers. And so we have around nearly 300 sites globally. And so we serve both the military as well as the commercial aviation market. Okay, so that's about Collins Aerospace. Just last few words, I will take another 2 minutes. Okay, this is on the systems engineering. So right now, as engineering professionals, you guys have chosen your specialization in your engineering education. So some of you are in electronics and communication, and some of you are from computers, and many of your friends are from different streams, mechanical and all that, right? But when it comes to the industry, so now the India as the economy based on the technology is moving towards a product-based economy. So earlier, India started the IT revolution, and so they established themselves as a service provider in the industry, because the nature of work that we used to do in the earlier days, if you see in the IT companies and other associated companies, they were of service in nature. So there were multinational companies all over the world, and they used to define a set of tasks or activities, and with a defined scope, and they used to assign to us, and we used to just perform that activity and deliver that. So this is called a service-based model. Okay, but so now we have gained a lot of experience and expertise, having worked on those service-based projects and the industries. So slowly the industry is moving towards product-based economy, wherein we come up with our own ideas and our own products, rather than just delivering the services to the other companies. And you can see that the startup ecosystem is emerging all over India, including Tamil Nadu and Karnataka. There are a lot of new startups coming up with innovative products. Okay, and so the discipline, so which handles this product development, we in the engineering community, we call it as systems engineering. Okay, so in order to develop a product, we need the contribution from multiple disciplines. So it is not just the electronics engineer or a computer engineer or a mechanical engineer. So depending on the nature and type of the product, so we need to have the contribution and the expertise of different engineers. But we need somebody who coordinates and who defines the concept of the entire product, what basically it does from the user point of view. What does it mean in the technical terms? What are the technologies involved, and what are the activities involved in order to achieve or realize that product? And in order to perform this activity, what kind of specialization or what kind of expertise do we need, and who can do that? What level of skill set is required? So these things are analyzed and defined by a systems engineer. So we call the person who does all this activity as systems engineer, so who is responsible for defining the concept of the product and also define the activities and also identify the people who can perform those things, and also technically mentor each of those people in working in a coherent way to achieve the or realize the product. So this systems engineering is picking up momentum in India now. There's a lot of focus by the industry. Many companies are focusing on developing talent and developing systems engineers for their business. So in this regard, so we have an international community called International Council of Systems Engineering, who is promoting the discipline of systems engineering across the industry as well as in academia. And we have an India chapter, okay, so of which I am a part of. I am the secretary of Infosys India chapter currently. And so we have been conducting a lot of initiatives for the academia as well as industry to develop the competency in systems engineering. For the academia side, basically we developed the curriculum on systems engineering. We have proposed and helped the various universities, including IITs, to introduce a specialization on systems engineering as part of their curriculum. Okay, so that is one activity. The other one is we also help developing this competency in the engineering students by providing the mentorship and also by conducting a few awareness sessions and also trainings. And so for this, we have a concept called Systems Engineering Students Club. Okay, so basically we discuss with the individual institutions and come up with a plan for starting a Systems Engineering Students Club. The students who are interested in can enroll in that, and so they'll be getting an opportunity for participating and getting the mentorship of the Infosys India chapter, through which they'll be able to understand what is systems engineering is all about, and also they can go through some kind of informal training. And we also provide the mentorship and training for a formal certification. The Infosys provides internationally recognized certification in systems engineering. Okay, so on behalf of India chapter, we also provide the mentorship and guidance to the students in achieving that. So the student chapter can do a lot of things, and they can also prepare the young engineers for taking up the challenges in the industry, and also to play the role of a successful systems engineer. Okay, so with this, my proposal to the leadership and the administration of Eshwar Engineering College is to consider this proposal of initiating a systems engineering students club, okay, in which we will be able to offer support from Infosys India chapter. So Dr. Raja, maybe you can, if possible, you can discuss with your management, and if there is a willingness, please let us know, and so we can take this forward.
Sure, definitely. I will take this to the management through the HOD, and I'll let you know regarding that club activity combining with Collins Aerospace. Okay.
Not Collins Aerospace. Actually, it is with the Infosys India chapter.
Okay. Fine.
Yeah.
Okay. So, dear participants, do you have any questions? You can raise the questions if you want to share anything. Dear participants, do you have any questions? I hope there are no questions as from the participants as concerned.
Sure. Okay. You can contact me in case if you have any queries. You can contact me through this email.
Sure.
Okay, so I have provided both my official and the personal email. And for any personal queries, please write to me on my personal email ID. And for any official interaction, you can write on my Collins email.
Sure. I hope the resource person have given an insight, deeper technical in domains which covers almost 3 to 4 domains: wireless networks, networking, then satellite communication, and avionics. So, with this note, I'll like to propose the vote of thanks at this junction. So, I take immense pleasure in proposing the vote of thanks. I thank the management, our principal ma'am, Dr. Sudha Mohanram, our director sir, Mr. Rajaram sir, and Mr. Kannan sir, Kannan Narasimhan sir, director IT, for supporting in organizing this event. I also thank our deans R&D and Dean Academics for their consistent support. I also thank our beloved HOD, Dr. N. Shanmugasundaram sir, for providing a constant support, and he is our guiding force behind all our academic activities. I also thank all the heads of the department and the fellow faculty members who stay with me in organizing this event in a grand success. Finally, I will thank all our student friends for their participation in the Knowledge Fest. I thank you one and all for giving me this opportunity to organize on behalf of Sri Eshwar College Engineering. I want to give a special thank to our resource person, Prasanna Ramamurthy. In spite of his busy schedule, he gave me a consent in providing this webinar, which is really a technical first for the students at this hour. I thank you, Prasanna. Thank you. Yes, thank you for joining with us.
Yeah, thank you very much, Dr. Raja. And so again, I would like to thank the management of Eshwar Engineering College, and my thanks to all the students who had the time to listen to me patiently. I think I have taken a little more time than what is planned. And
not really. Okay. Thank you, Prasanna, for joining us. Thank you once again.
Thank you.